relationships between data. So this is the start of our linear relations unit where things really start to take off for us. The first thing is that understanding that a relation is just comparing two elements. It's taking two things and comparing them somehow. And so that's called a relation. We have a lot of ways to represent relations. We could represent relations with words, right? So I could describe two things as attached to each other. And then there's a lot of mathematical ways to do it. The first way we do it is a table of values. A table of values shouldn't be that new to you. So table of values, let's start here. A table of values is a way of connecting two pieces of data. In this case, they're representing S and C. We don't know what S and C are. Right? It's just two pieces of data. And when you see them in a table of values, that means when S is 20, C is 10. It also means if you go to the second row that when S is 30, C is 9.1. And so on and so forth. So anything that's side by side is connected. S is 80, C is 7.6. That's them comparing two sets of data using a table of values. You also could use something called an ordered pair. An ordered pair is something you've seen a lot of. It's how we usually represent points on a graph, right? X and Y. In this case, they've done it again, but with S and C. And you'll notice that they paired them up the exact same way you saw them in the table of values. But instead of separating them off into a table, they just made it a nice little set of brackets. When S is 20, C is 10. They put them side by side and in a set of curl brackets. When S is 60, C is 7.6. 60, 7.6. Right? Two ways of representing the same. These are two of the most common ways that you see data represented. A third way, which you don't see a lot of, a little bit in science, I think, is called a mapping diagram. The reason you don't see it very often is it can get a little confusing, a little disorganized. Mapping diagrams take all your possible S values, all these guys, and they bubble them. They put them in one big bubble. And they write them from lowest to highest, so ascending order. It's increasing. Then they take all the possible C values, all of these guys, and they do the same thing. They write them in one big bubble. And just like the other one, they write it in ascending order. So from lowest to highest. And then they use arrows to connect the two things. So they say, if your S is 20, your C would be 10. And they connect it using an arrow. See how it gets a little confusing, a little convoluted in there, and it gets pretty messy. That's why you don't see a lot of mapping diagrams. Every once in a while you do, though. So it's important that we talk about it just in case you see it. Science likes to use it for comparing like animals and stuff like that, like cross-referencing things. Another example, if S is 60, that means C is 7.6. 60 points to 7.6. All right, the last one that we're going to talk about is a graph. And you've seen a graph a lot. Right? This should be definitely one you're used to. And graphs have points on them. And each point represents two things. It represents how far left or right you've gone, and it represents how high up or down you've gone. So for instance, if you look at this point right here, green, that point went a certain distance to the right, 30. So it went 3 to the right, and then it went 9.1. It represented usually with an order. Okay, so that point on the graph represents the ordered pair. The ordered pair is the same one you found over here, which is also the same one you found on your table of values. Like all of these things are just the same way of representing something different. Yeah, in case there's no question, for sure. They're all just representing the same amount of data in a different way. Which is really just comparing two things. And in our case, it's S and C. We don't know what those two things are, but it's representing. Any questions about those four things? You should have seen them all before. Maybe mapping diagrams, kind of like, oh, I don't remember that. All right, mathematically, we could represent all four of these things using an equation. And that's the equation right there. That equation links C and S. And we're going to talk about how we discuss equations and terminology we use for equations. Because we need to always be on the same page. So if I'm asking you for something, it's important that you're getting the same thing. You'll notice that the S's were always coming first in things. And they went side to side. It doesn't have to be the letter S. It's just that the first thing is always first in all of them. And it's always the one that goes on the horizontal. The second thing is second in all of them. It's the second thing in your order of pairs, second thing in your table of values, second thing in your mapping diagram, and it's your vertical on your graph. And so it'll always follow that pattern. The letters could change, right, but it's always that pattern. The second things are always second, and they go up and down. The first things are always first, and they go left or right. Right, discussing an equation. Now the first type of terminology we use is dependent and independent to represent an equation. When you have an equation, you should have it so that if you were to draw a line through the equal sign, it should be cutting the equation into two parts. One part should have a letter all by itself. The other part should have a letter and then a bunch of numbers. The letter that's all by itself, we call the dependent. It's dependent on whatever happens on this side of the equation. The letter that's on the other side of the equation, we call the independent variable. It's a number that we can choose or it's given to us. And then whatever number we choose or given to us, it creates a number for my dependent. And we'll do a little bit of that in a little bit so you can understand. But at the end of the day, the terminology of dependent is the variable by itself, independent is the variable next to letters is important. It'd be nice if they always use the same terminology, but they don't. So there's two other terms to represent the same letters. Those terms are input and output. And those are the terms I'll use more often. Okay, so input and output. If you took an equation, this new equation right here, and I was to cut it in half where the equal sign is, the letter that is by itself, I call that my output. The letter that is with all the numbers, I call that my input. In all those ways we learned on the slide before. So we learned about like mapping diagrams, and we talked about table of values, and we talked about ordered pairs. The input is always the one that comes first. The output always comes second. In terminology-wise, for some reason, like that makes sense to me. If I choose something to put in, and then I get something. So the input would come first, and then I would get an output as a result. So for some reason, in my mind, that like makes sense. I know it probably doesn't in a lot of people's minds, but for whatever reason, that terminology really clicks for me, which is why I use input-output as my term. The other thing that you're going to hear me say a lot is I won't maybe use the word input. I'll say, what is your x value? The x value is the input. Sure, in this question, the letter actually is x, so that's nice. But this could be any letter I want it to be, and I might still refer to it as x. The reason I still refer to it as x is because the input is what goes on your x-axis, your side to side, no matter what the letter is. The output, no matter what the letter is always my y on my graph, my up-down, my y-axis. So you might hear me use that same terminology. So even up here, instead of independent, I might call that my x variable, and I might call this my y variable, because my independent goes on my x-axis. My dependent goes on my y-axis. They've also put it here, they've shown you the second coordinate on the ordered pair is your output. The first coordinate on an ordered pair is your input. Like they've shown you a little bit of things there, and they've written it out nicer than I have. All right, how inputs and outputs work. On the next slide, we're going to be given a table of values. In that table of values, they've given you some input values. They want to know what the output is for each one of those input values. To figure out what the output is that matches each input, you have to put those inputs into the equation they've given you. So you need to take each input and substitute it into your equation to calculate your output. I'll do one with you, I'll do two with you, and I'll let you try to do three of them on your own. So if my input, or my x, is -2, I need to substitute that in for my x value in my equation. That means I now have y equals 2, and instead of x, I'm going to put my input value, -2, minus 5. So notice that the equation stayed the exact same. The only thing that changed was instead of x, I put an input value. The only thing that changed was the x. Everything else is the exact same. So that means if I had negative signs, if I had square root signs, if I had exponents, those things would all stay the same, and only the letter itself changed. I also used brackets. Your calculator can also do brackets, so that's probably important to learn how to use them. The reason I'm putting brackets is sometimes crazy things happen when you multiply and you substitute. So the brackets help make sure that it stayed together as a -2. From this point, I want to figure out what my output is. I no longer have anything but numbers on the other side. So I can put that into my calculator. I would put it in exactly how I see it. So in my calculator, I would put in 2 bracket -2. The negative symbol is the one beside the decimal. And then I close the bracket. And then I go minus, which is the subtraction sign, 5. And I hit enter. And you should get an answer of -2. That means if my input is -2, my output for that equation is -9. Any questions about that? Did you try it in your calculator? It's important to try these things. So if you hit a wrong button and all of a sudden you get -7 as your answer, and you're like, why did I hit that? Now's the time to try it. Make sure you actually use the brackets, it's important. You could also do those calculations slower by using BEDMAS. You could do the multiplication, 2 times -2, get an answer, and then you could subtract 5 and get an answer. And you could break it down into chunks as well. All right, we're going to try it again for the second one. So it says I have an input of -1. I need to put that into my equation to figure out what my output is going to be. So y equals 2 instead of x. I'm putting -1 and then -5. After you do your input, you should have no x's left.
So, what's the ordered pair?
Oh, sorry, I didn't write that. So the ordered pair would then be -2, -9. The input always goes first, the output always goes second. And if you were to do that for a mapping diagram, the x would be in the first bubble, and the -9 would be in the second bubble. And the arrow would go from left to right. Right, now that I've done my input, I'll do the same thing. I'll take this thing, and I will put it right at my calculator. 2 bracket, I use the negative button, which is beside the decimal. -1 bracket, -5, that's a minus symbol, so it's above the plus. And that will tell me that y equals -6. So for an input of -1, I get an output of -7. To write that as an ordered pair, you just go input first, output second. I want you to try to find the next 3 on your own. So put all those values into your equation to find your outputs. Yeah. All 5 of those are written down. You should have them all. Inputs and outputs are very useful, right? You can always put context into these questions. We don't yet. Your practice booklet does a couple times, so you can try it out to see what it's like. But equations could represent a lot of things. So it could represent the height of the sun at any given time of day. So if I input a time, I could figure out the height of the sun. Input time, output height of the sun. I could do all kinds of things like that, where you have an input, some sort of value, and you figure out your output. Like you could do, you could do how far you've traveled, how long you've been traveling. You input how long you've been traveling for, that'll tell you how far you've traveled, your output. And these things do relate to each other in real life context, we just haven't done it. Right now we're just talking about here's an equation, put something in, get something. On the next slide, that table of values is completed for you up here, so it should be the same one as we just had on the last page. And now we're going to try to use this table of values and these ordered pairs and transfer them onto a graph to see what it looks like. So part A says plot the ordered pairs found on the previous slide. The x-axis is always your inputs. The y-axis is always your outputs. That means on a graph, your input is telling you how far left or right to go. Your output is telling you how high or low to go. If it's left, it's negative. If it's right, it's positive. So my first point is at -2, -9. That means I need to go 2 to the left, 1, 2. And I need to go 9 down. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's my first. My second ordered pair is at -1 to -7. So I need to do the same thing. I need to go. First ordered pair tells me how far left or right to go. -1 to the left. -7 tells me how far up or down to go. -7 means go down, so down 7. 1, 2, 3, 4, 5, 6, 7. That's my second point. I want you to put the next 3 ordered pairs on the graph on your own. So put those ordered pairs on your graph. Make sure you're doing it right. So part A was to just take those ordered pairs and put them on a graph. And that's what we've done. So we've actually taken some data, some relation, and we've shown them as an equation, we've shown them as a table of values, we've shown them as an ordered pair, and now we've shown them as a graph. But we could have more to this, right? We could do more inputs. I could have an input of 3. And that would give me an output of +1. That would give me another ordered pair of 3 and 1. And I could keep going. This list could be infinitely long. Right? I could choose a lot of inputs. I could even choose some crazy decimal ones. So I could do 4.5 and whatever that equals, and it would give me some ordered pair. Graphs can represent all of those points. Table of values, ordered pairs, that's too difficult to write every single possibility of. To do it graphically, what we do is we take those points we just had and we connect them with a line. And we just draw that line on both ways forever. So if I was to draw a straight line connecting this data, I would just take that dot and try my absolute best to go straight. Actually, that might be the best I've ever done. So that was pretty good. You should all be proud of me. For you guys, the best way to do it is to take your calculator. The battery cover on the back is a really perfect flat straight edge. So that's what most people use instead of carrying a ruler. You won't have to measure anything in this class, but you will have to draw straight lines. So that's a nice, easy way. Other people use debit cards, their license, whatever works for you, as long as you're drawing a straight line. So I want you to draw a straight line that connects all those dots. The back of the calculator is what's probably used the most. Because it's decently small, it's perfectly straight, and it's flat. You should all have a nice straight line, straighter than mine, although that's pretty good. I'm pretty proud of myself. So, the reason that graphs are useful is that you can then look at any input, any output you want, and find where that point is on the graph. So for instance, if I looked at this point on the graph right, let's say right here, that point is at 8, 9. That's definitely not. That means that if I had an input of 8, I would have had an output of 9. And I didn't even have to calculate it. By just finding the point on the line, it told me what it was. That's what your calculators actually can do, is they can take every single point that exists and draw them in a straight line. And then you can put in your calculator, okay, what's the output when the input equals 2? And it'll automatically tell you. And you can do it for decimals, you can do it for anything. You can also do a lot of other really cool things. And we'll learn about those probably late this week or next week. Today what we're going to do is we're actually going to use these use these graphs by hand. And we're going to try to use the graph to determine the value of y when x equals 6. So you have to find somewhere on this blue line where x equals 6. And they want to know what's the y value. Graphically, that means they want you to figure out if you go 6 to the right, so let's go 6 to the right, 1, 2, 3, 4, 5, 6, how high up or how far down do you have to get to be on the graph? Right? That's what output is. Height, so either high or low. So if I went 6 to the right, how much further up do I have to go to get to my graph? And the answer is I have to go, that's 6. 6 to the right would give me 6 up. So my value of y when x equals 6, y would equal 6. Because that's the point on the graph that has an input of 6. You see how that works? So you put an input into it, the graph, to find where the output is on that line. You could also do it vice versa, which is kind of nice too. So the next question says, use the graph to figure out the value of x when y equals 3. Now they're saying your output equals 3. What input would give you that value? They're saying you've gone 3 up. 1, 2, 3. How far to the left or right do you have to go to get to your line or your graph? In this case, I would have to go 1, 2, 3, 4. Let's call it 4. Let's say that. I would have had to go 4 to the right to get an output of 3 up. If you're given a line, I'll always give you a line, and it'll work out. If I ask you to draw something, as long as your drawing is accurate enough, you'll be good. It'll work out. But that's why it's important to make sure you are drawing with straight lines all the way through. Because it would work if you drew a straight line that went right through all those intersections. Mine's a little bit off, actually. You can see it should be a little bit to the right. You can see I kind of missed some of my points. It should be more like that. But that's why you get into those like half spots where it doesn't work right. So for my graph, if I wanted an output of 3, so up 3, I would have had to do an input of 4. So that means x would equal to 4. And you can do that for any given number that you want. As long as it's somewhere in your graph, you're good. Any questions about how to read a graph, how to find points on a line when given an input or an output? It's a very useful skill. It's going to come in handy a lot, especially in Unit 6 and especially in Math 20-1 or 20-2. So being able to read a graph, input a value, or find an output of a value. All right, you have